So for Monday's assignment, I'm going to use two separate videos to demonstrate the techniques and the very problem we're trying to solve. So in the first video, I'm going to demonstrate the concept. Okay, primarily, I'm going to demonstrate the concept about the specific way of approaching a problem. Okay, so these are three things I'd like to solve. I'm trying to show you what this methodology is capable of. Okay, and then we're gonna apply it to more operation supply chain problems in the second video. So let's first take a look. You're all familiar with this. Okay, we've done this together. In this particular problem, we're trying to minimize the total cost by adjusting the inventory level. So a lot of you did brute force approach and arrived to the local solution. For example, a lot of you have identified that 80 is actually the total minimizing ordering quantity for this particular problem. And if you look at this, the first column shows the level of inventory. The second column shows the total resulting the cost. So if if we try to do it in a fancy way, if we enter the graphics, right? I don't know if that's obvious to you. So here's a certain point. Here's a little point that make your total cost lowest. So that is 80. Okay, that is 80 for this particular problem. But I also during the class I mentioned that the actual theoretical inventory quantity is actually 87 instead of 80. The reason why the 80 currently give us the lowest total cost is because we only have 200 iteration. So if we increase this number of random number to, let's say, 2000, maybe you'll be seeing that 87 becoming the total cost minimized inventory level. But anyway, so I'm going to take a slightly different approach to solve this problem. I demonstrated this once in the classroom last Wednesday. I'm going to do that one more time. So here I'm going to data solver. Okay, as you can see from this setup, solver is usually helping us to obtain minimizing. So in this case, we're minimizing the total cost, which is situated in Q2 cell. We're trying to minimize Q2. We're trying to minimize. Of course, you can maximize. Okay, we'll do it later. But we can minimize. We need to minimize the Q2 by changing C17. That's exactly what it is here. So we don't actually need any constraint, but just to show you the concept, I added one constraint here. Let me delete it and add it one more time. I want this quantity to be integer. Okay, it could be fraction number, but I don't need that. I just want this to be an integer. Okay, so that's what this means. You can choose any other conditions, but this is what we need at this time. You click OK. So I think by default, the solver is considering this number as a positive number, but what I'm going to do is I'm going to do this anyway. Okay, it has to be at least greater than 1. So this part is called constraints. Okay, so you consider this tool as a search tool, a tool that help you search through solution space and identify a solution that satisfies the condition that's listed in here. So you click solve. Okay, so you see it's maintaining current solution. It looks like obviously 80 is the best solution. So I'm gonna change it to 34. Obviously this is not the optimum, but I'm going to run that tool one more time. Solver, all the settings will be the same. I didn't change anything, I don't have to. You see, so after a certain amount of time, so solver has performed 5 iterations. So using 5 iterations, it has arrived to a current optimum solution, which is 80 unit, which is also the total cost minimizing solution. So see, we have confirmed in here. Okay, so I'm going to demonstrate one more example. So in this particular situation, our demand pattern is not exactly normal. As you can see from here, our demand pattern is actually a uniform distribution. So we don't exactly know what is the theoretical level of inventory that minimizes total cost right here. So I don't really know. So maybe 20, maybe 30. I'm not sure. But I do have this over rich cost and under rich cost, and it looks like a critical fractile is 60. But again, what does it mean for a uniform distribution? So here we have learned how to deal with a normal distribution, but uniform, this is new. So I'm going to take advantage of solver to solve this problem one more time. So in this case, we are minimizing the M2, which is our grand total cost, by changing the value of cell in B1, and I'm going to add the same constraints here, okay? So it has to be integer. So I'm not going to add that positive greater than 1 constraints, because I think it's automatically assumed. So I'm not going to, here, make unconstrained variables non-negative. So if you do not put a constraint on this variable, it's going to consider that as a non-negative. So again, solve. So it's 127. That's currently the optimum solution for this problem. So I actually know what is the theoretical optimum level, because for the uniform, there is certain calculation you can do. It's actually 120. Okay, for now it's giving 127, which is somewhere close to the theoretical optimum. Again, I'm replicating this using 800 different random number, but as you increase that indefinitely, I think the solution here is going to close to the theoretical optimum. But anyway, let's move on, and let's solve a somewhat different problem this time. So okay, for example, we are asked to choose 4 projects that maximizes your gain. Okay, so here project 1 has expected outcome of this amount. If you decided to go with this, you choose 1. Okay, if you don't want to choose this, you put 0 here. Okay, so project 2, this is expected outcome, so forth. So you need to pick 4 that will maximize your gain. So at the end of the process, you probably will see something like this. So you choose 2, 5, 8, 10. This combination is believed to have the most gain. But here we have additional constraints that makes this kind of problem a little bit more sophisticated. For example, 2 and 8 cannot be chosen together, right? Only one should be chosen. Only one should be chosen. So 2, for some reason, 2 and 8 should not be chosen together. So for example, in this case, it's not allowed. For some reason, you either need to choose 2 or 8, but you can't choose them at the same time. So 3 and 7 must be chosen together. So 3 and 7 has to be chosen together. So, and 10 must be chosen no matter what. So in other words, I have added additional constraints to make this problem a little bit more sophisticated. Okay, so eventually when I calculate the total expected outcome for this particular projects, what you need to do is your calculation will look something like this. This multiply your choice plus multiply your choice plus multiply choice. You can keep going on, okay? So for example, C2 indicates your decision. If C2 ended up having value of 0, it means you did not choose project 1. If C3 becomes 1, it means you actually chose project 3. So after you complete the whole thing all the way until let's say all the way until, I'm actually skipping a lot, okay? Because this is not the formula I'm going to use eventually. This is too much, there's too much calculation in here. I'm not going to use that. There is actually a more convenient Excel formula that help you do that, okay? So, but anyway, theoretically, this should be your function in order to calculate total expected outcome from this particular setting. So it's basically matrix, right? You multiply this with this and then this and so forth. So for that, you have sum product. Okay, sum product. So for sum product, the first component is this range. Okay, and separated by comma. The second range is this. I think you better have exactly same length of range. So in this case, it basically tells you to do whatever I tried to do in the previous step, which is B2 multiplies C2 plus B3 multiplies C3 plus B4 multiplies C4 all the way until B11 multiplies C11 and so forth. Okay, so for now, let's take a look. So if you see, this is changing. Okay, so you may enter 2 here, but this is not actually allowed. You can technically enter 2, but it's actually meaningless, and you're not allowed to do that. Okay, so for the yellow cells, all you need to enter is either 1 or 0. That represents your decision. Okay, now let's utilize solver to have this choice process. Let the solver work on this choice process. Okay, let's actually remove this constraint. I think it's going to make the problem unnecessarily difficult. Okay, for now, I think I'm almost ready to implement the solver. Okay, let's take a look. Okay, let's take a look. Yeah, but for the convenience, what I'm going to do is I'm going to do this additional step. 2 and A cannot be chosen together. Only one should be chosen. Only one should be chosen. So what I'm going to do is decision for 2, decision for 8. Okay. For now, it's 0. But I'd like to make this value less than 1. Okay, so at least it's not going to be 2. So it's okay that you don't choose either 2 or 8, but you ever pick 2 or 8, but you can't really pick them at the same time. So with implementation of this, right, it could be 1, right? That's permissible, but it cannot be 2. It could be 0. But 0 means you won't pick anything between 2 and 8. If it's 1, you may have picked 2 and 8. So what I'm going to do is I'm going to color it with a pink to indicate this is a constraint. Oops, okay. Pink to the cell. So data, solver, okay. So we are maximizing C14. Yes, C14, yeah. C14 is our total maximum outcome. And it's maximizing, it's not minimizing, right? And let's take a look at our constraint. So for the constraints, what I'm going to do is I'm going to highlight this yellow part, which is our decision variable. I want it to be binary, bin, okay? So I want a binary, that's one condition, one constraint. So for this value right here has to be less than or equal to 1. So there is one more interesting condition here. 10 must be chosen no matter what. So 10, it has to be equal to 1. So let's click OK. So first constraint says that C11, which is 10, must be chosen, and C20 less than C20 less than or equal to 1, which is this particular cell, will force us pick only one between 2 and 8. And this binary condition says that it's, when you change the variable, it has to be between 0 and 1, okay? So that it represents our choice, decision choice. So let's click. Okay. Oops, let's take a look. Oh, you see, I forgot to implement one condition here. So you see, it says only 4, you can choose 4 projects that maximize our gain. So it means that our total choice should not be greater than 4. It has to be exactly 4. So summation of this has to be exactly equal to 4. So I'm going to make it as one of my condition. Okay, this has to be equal to, to 4. Yeah, let me add that back. So this is totally normal in terms of linear programming. You kind of always have to add some of the constraints back after you discover you have made simple mistakes like this. So click OK. So now I have added additional C13 equal to 4. It means that I'm only going to pick 4 here. So let's click solve. Yeah, it took a little longer, but it picked. Okay, so it picked 1, picked 7, picked 9, and 10. Did it pick either 2 and 8? No, it did not. Okay, no, it did not. So if you look at it, this is the Excel's choice. I think it's pretty plausible. Okay, mostly it picked those larger values. So I was wondering why it didn't pick 3, but it instead picked 7. I could have picked 3 to get a bigger value. In that case, one thing you can do is see if you can run it one more time. You can run with a different engine to see Excel can improve its solution. Okay, so now as you can see, as I pick a different search engine, which is Simplex, okay, you have different search solutions here. So I picked Simplex, it has improved 1, 1, 1, 1. So now it looks like this is even bigger than the previous solution result. It's more plausible. This is better solution. So it's a very normal process. You do a lot of try and error using the solver tool, see if Excel can improve its previous solution. So I just did it like this. So I'm about to conclude the very first video. In general, I'm trying to show you what the solver is capable of and what type of problem solver is capable of solving. As long as you get that correct, I think you're ready to step into the second video. Thank you.